This homework problem is based on an episode from my criminal past when I was a Peterman or a safe cracker, and it relates to the combination of the safe in which the exam papers were kept, which is how I got where I am today. So the safe is controlled by 4 switches labeled S, T, U, and V, and each of these switches controls a signal, S, T, U, and V. When the switch is in the down position, like this one, it sends a 0, and when the switch is in the up position, like this one, it sends a 1. We're told to use 4-bit 2's complement notation to interpret these 4 bits of a signal, and we're asked which decimal number is indicated by the above setting. So what do we have in 4-bit 2's complement? Well, the places of the number have, as ever, doubling values. So rightmost we have the 1s, next the 2s, then the 4s, then the 8s. But what makes it 2's complement, signed representation, is that the leftmost place value is negated. For part A then, we can see that we have no -8s, 1 4, no 2s, and 1 1. That's to say we have 4 plus 1, which makes 5. For part B of the question, we're told that to open the safe, we have to construct a circuit which actually delivers, checks rather, that we're in the correct release configuration. So we have to deliver a release signal which is 1 only when S, T, U, and V are in the correct configuration. And my informant, who is known in the criminal trade as the bellman, has analysed the circuitry and told us that the correct combination is -6. So we need to build a circuit which detects -6. Well, first of all, we're going to need to figure out what bit pattern is -6. Well, here, in order to make -6, we're certainly going to have to use the -8 to make a negative number at all, and then to get to -6, we're going to have to add the 2. So we could just stop here and write down this bit pattern. Another way to see that this is the right answer is to use the procedure for negating a number in 4-bit 2's complement representation. You write down 6 as a 4-bit binary number. You flip the bits, thus subtracting the number from -1, and then you add 1, and that gives us 1 and 1 is 0, carry 1, 1 and 0 is 1, 0 and 1, the same answer. Okay, now we have to build a circuit whose inputs are S, T, U, and V, and whose output is the release signal. And the release signal must be 1 exactly when S, T, U, and V have this bit pattern. So what we need to do is to build a detector for this bit pattern. How do we do it? Well, we write down the bit pattern, and then we turn the 0s into noughts, and wire them up, and then we check. So these will check that each bit is the way we want, and then we can check that they're all the way we want by building by connecting them up with AND gates. Of course, we're asked to build this circuitry from NAND gates, so we had better build these two components, NOT and AND, from NAND. So let's remember how to do that. We make NOT by feeding the same signal to both inputs of a NAND gate. So when 0 comes in here, then we have negated 0 and 0. So that's negated 1. So negated 0, which is 1. And when we have a 1 coming in here, then we would have AND of two 1s. Negated gives us 0. So this behaves like NOT. To make AND, on the other hand, we take a negated AND and we negate it back with NOT. So we built the release circuit from NAND gates as a detector for the bit pattern using NOT and AND. Moving on to part C of the problem, the bellman has also found the circuit diagram for the alarm circuit. And it's built, again, connecting S, T, U, and V, the controls for the safe, only this time to the alarm. And we need to make sure, as we try and open the safe, that the alarm stays at 0. So it's worth thinking about when this alarm will go off. We have an AND gate here, so the alarm goes off if both something and something. Let's look at the two somethings. Well, one side of our AND is connected to a three-way OR on T, U, and V. So both any of T, U, V is 1. And on the other side of the AND gate, we have S and V XORed with that then negated. Now, XOR tests to see if its two inputs are different. When you negate that, you're testing to see whether those two inputs were the same. So the other condition is that S equals V. Let's just do a quick check over here to see whether the alarm is going off already. Well, we can see that one of the conditions is true because both T and V are 1, but the other condition, namely that S is equal to V, that condition is false. So thankfully, the alarm is not already going off. The police are not yet on their way. So let's see if we can keep it that way and figure out how to get where we're going. Our current configuration is 5 or 0, 1, 0, 1. So I'll just draw that in a blob, and then I'll draw spokes from the blob to figure out which ways we can go. So what would happen if we changed the S signal? Well, then we would make S equal to V and fulfill the other condition. Both conditions of the alarm would then apply. So if we change S to 1 here, the alarm goes off. However, as long as we keep S different from V, the alarm will not go off. So certainly we could flip T, and that would take us to the configuration 0, 0, 0, 1, also known in 2's complement as 1. Or we could flip U So that was T, this is U. Flip U and get 0, 1, 1, 1, and that's also known as 7. And at the moment we don't really know which is a good move, but it doesn't matter as long as we map out the possibilities. Okay, let's see where we can go from this one. Well, if we flip U back, we get to where we came from, so that's no good. If we flip S, we set the alarm off, because we've got some 1s here, and we would be making S equal to V. Okay, so what else can we do? We can flip T, and that will get us to 0, 0, 1, 1, also known as 3. So that was the flipping T. We said flipping U would take us back. Flipping V would again set the alarm off. So this is our only new possibility. Now what happens here from this position? Well, if we flip S, we set the alarm off. If we flip V, we set the alarm off. If we flip T, we go back where we came from. If we flip U, we end up at 1. So even though going this way was a bit of a wrong turning, it didn't matter because we end up forced to this position anyway. So now let's think what we can do from here. Well, if we flip S, we still have a 1 here, so that will make S equal to V, and V will be 1, so the alarm will go off. We had better not flip S. T and U would both be backward steps, so we had better flip V. And that will take us to 0, 0, 0, 0, also known as 0. So now what happens? You'll notice that S is equal to V, but the alarm did not go off because at the very same moment we made the S equals V condition true, we made the any of T, U and V being 1 condition false. So at this moment we've switched to the other condition being critical, but we've got away with it. So now what happens? Well, if we flip either T or U, we are setting the alarm off. If we flip V, we go back where we came from. So our only choice, and it's a good choice, is to flip S. And that takes us to 1, 0, 0, 0, also known as -8. That was flipping S. And we can just check, S is different from V, no alarm. And that's great, because we're now 1 step from home. We're trying to get to 1, 0, 1, 0, also known as -6. And we can get that by flipping V. Flipping U. Thanks for my prompter. That means the path that works, after we've drawn the map, we could just read the route that worked, is T, V, S, U. We've opened the safe, we haven't set the alarm off, we've stolen the exam questions, and we're all going to pass.